All right, let's get started. First of all, to whoever said last time that I wasn't recording and I said, yeah, it's recording. Well, you were right. I was wrong. Sorry about that. Only 2 minutes of last week's lecture, last class's lecture recorded and went to YouTube. I'll try to be more careful about that. Second, as usual on a Wednesday, I'm going to start by going over a homework problem. So it's hard to run polls in Zoom with two devices. Instead, just type into the chat which problem you want me to go over, and I'll see what's most popular. Come on, this is something where everyone gets to vote. So pick a problem number. It's not just my usual suspects who signed up for the premium plan on Patreon. Everybody gets to ask a question. All right, looks like 4 and 5 are pretty popular. So first of all, let's talk about 4 and what it was asking. 4 was just asking which of these can be written as the gradient of a scalar field. And we discussed last time that if f is the gradient of some scalar field S, then the curl of f is equal to 0. And I also stated but did not prove that that is a sufficient condition, meaning that if the curl is 0, then it must be the gradient of a scalar field. So it really just came down to figuring out which of those 5 have a 0 curl. Let's start with the curl of f of r hat. All right, now curls in spherical coordinates are complicated. And we didn't derive those formulas because you go through dozens of tedious algebra steps and you get an answer, but the process is not terribly meaningful. Instead, I just said we're going to focus on using them. And on Friday, you were calculating curls in spherical coordinates. The curl of any function in spherical coordinates can be written as, I'm going to copy from the book right now, curl of A is 1 over r squared sine theta, r hat, r times theta hat, phi hat, then derivative with respect to r, derivative with respect to theta, and derivative with respect to phi. And then we've got a sub r, r a sub theta, and r sine theta a sub phi. Any questions on how I set that up so far? This is just straight from the book. All right, now if the function only has an r point and only depends on r, then derivatives with respect to theta and phi must be 0, and the theta and phi components must be 0. And so what I've got is that the r component of the curl will be, let's see, 0 times 0 minus 0 times 0, that's 0. The theta component will be, the derivative of 0 is 0 minus 0 times AR, well, that's 0. And then finally here, we'll again have the derivative of 0 minus another 0. And so that curl can only be 0. And you're probably thinking, wait, when can you replace a derivative with 0? When you know in advance that it's 0. If I know that something doesn't depend on a particular variable, if I know, more importantly, if I know that nothing in this formula depends on theta, then I'll just replace all the derivatives with respect to theta with 0. If I know in advance that nothing in this problem depends on phi, then I'll replace the derivatives with respect to phi with 0. And at this point, someone will say, but what if like some of them are 0 and some of them aren't? Well, if some of them are 0 and some of them aren't, then you can't just guess in advance. Then you have to churn through the hard work. Any questions there?
So is it always the case that the divergence, if we do have a divergence, then the curl is 0?
If we have a gradient, the curl of a gradient is 0. If a vector field is the gradient of a scalar field, this is something we proved last time. This part, the first part we proved. If f is the gradient of a scalar field, then the curl is 0. We proved that last time. It also turns out to be the case. I asserted the proof, and now when we start going over surface integrals instead of line integrals, I can prove it. But if the curl is 0, then it's the gradient of a scalar field. Let's look at the next one. I've got g of phi hat. So I've got some arbitrary function of phi. And it would be tempting to say, hey, last time we had something with only one component and it only depended on that corresponding variable, and the curl was 0. That must be the case. I'm just going to say, without actually checking it, that must be the case for any combination of variables. Nope, we're going to prove that now. All right, so let's find the curl of that. That is, again, 1 over r squared sine theta, r hat, r theta hat, phi hat. And then I'm going to put in the derivatives. And then I've got, well, there's no radial component, but there is a theta component. And because that formula, because the curl in spherical coordinates requires us to multiply the theta component by r. Oops, sorry, I put in the wrong one. It's not the theta one that's non-zero. There's no theta component, my bad, but there is r sine theta g of phi. All right. And even though the phi component of the actual vector field does not depend on r or theta, when we take the curl, we have to first multiply this because phi hat depends on r and theta. And so even though, well, phi hat depends on theta, why is my, I have no idea why my tablet just skipped apps. Okay, because we have a vector whose orientation depends on where we are in space, all of the formulas get a little bit more complicated. So now if I take the curl, 1 over r squared sine theta times r hat partial by partial theta r sine theta g of phi. Hey, there's something that depends on theta, so that's non-zero, minus r theta hat times partial by partial r sine theta g of phi plus phi hat, well, that determinant is 0. But what's just happened here is we have 2 non-zero terms in that curl. So we know that this function is that g of phi hat is not equal to the gradient of some scalar function. Questions on that?
Yeah, where did that r squared sine theta come from again?
That's just part of the definition of curl in spherical coordinates. The steps to derive it are done in chapter 10. It's a very tedious algebraic slog. So I'm just asserting it. And I'm saying that the curl in spherical coordinates is different, looks different on the surface from the curl in Cartesian coordinates because your unit vectors depend on your coordinates now.
Okay, thank you.
And for those who want the derivation of it, I understand that motivation. I do. There's sort of two competing considerations here. On the one hand, I completely understand the desire to know why. On the other hand, it is an incredibly tedious and unenlightening slog. So the answer to the why question is not some simple generalizable principle that you can then apply in other circumstances. The answer to the why question is 20 steps of algebra that in the end give you something that you can look up. And if those 20 steps of algebra were 20 steps that you're going to be doing again and again in many other circumstances, then they're worth doing. But it's 20 steps of algebra that you pretty much never do any other time. You derive this formula once and then you just look it up going forward. Other questions? All right, there's three more problems in problem 4. There's three more functions in problem 4. The third one, xy x hat plus xy y hat, that one you can just plug and chug. So I'm not going to go through that one. But the fourth one, sine phi, cosine phi, phi hat. Well, what could we say about this one? Based on what we've done so far, what could we do at this point to answer this fourth one?
We can multiply the one we just did by sine
We can what?
phi.
Say
We
it a
can
little louder.
We can multiply the question we just solved by sine phi and cosine phi. And
I know what you mean, but I wouldn't say multiply because we're not multiplied anything. The one we just did, g of phi was an arbitrary function. And we showed that in general, if g of phi is non-zero, then the curl is non-zero. We're not multiplying anything. We're just replacing g with these particular values. Then the final one looks messy. We've got minus xy squared x hat plus x squared y hat over x squared plus y squared to the 3/2, which looks really messy and scary. But we hopefully by now know how to convert from Cartesian coordinates to cylindrical. I'm just going to replace x with r or rho cosine phi and y with r squared, or y squared, excuse me, with r squared sine squared phi x hat plus rho cos squared phi rho sine phi y hat all over, and then this bottom is just rho cubed. So, and that should have been a rho there, my apologies. So I've got rho cubed up top in every term, rho squared was there, and that's rho. And so what I'm left with is minus cosine phi sine squared phi plus cos squared phi sine phi. Oh, and that should be x hat. That should be y hat. Still looks kind of messy, but every term has cos phi sine phi. So if I just pull out cos phi sine phi, I'm left with minus sine phi x hat plus cos phi y hat. And this is the unit vector phi hat. So lo and behold, the fifth one was exactly equal to the fourth one. It's just that the fourth one was written in cylindrical coordinates, and the fifth one was written in Cartesian coordinates. Any questions?
I thought that would the not minus sine phi x hat plus cosine phi y hat is phi hat times rho.
What's phi hat times rho?
Just the inside the parentheses. Because I thought phi had to be like over the square root of x squared plus y squared, if I remember from the activity correctly.
Phi hat is minus y x hat plus x y hat over square root of x squared plus y squared. Yeah, that's true. Which is minus rho sine phi x hat plus rho cos phi y hat over rho.
Oh, I see. Okay.
Other questions? Okay. Then let's pick up where we left off last lecture. Last lecture, I had finished by saying that the integral of the gradient of some scalar function dotted with dr from point A to point B is equal to f at point B minus f at point A. Because the gradient dotted with dr, this whole thing here is just delta f. So we're adding up all the changes in f as we go from one spot to another. Now let me point out a few other well, first of all, let me say that this line integral is important in electromagnetism because you can use it to calculate voltage. It's important in mechanics because you can use it to calculate work. But then another important line integral was a line integral around a closed path of E dot dr, which turned out to be minus the time derivative of B dot dA, which is a surface integral. And remember, this is E. We're going around this path, and then we're calculating the flux of B. And the interesting thing is that for these kinds of paths, we could do it for any surface. You might be thinking, well, if I got a circular surface, wouldn't it just be the flux through the circle? Well, sure, except who says that the surface has to be perfectly circular? What if you could say, well, yeah, but as long as it lies in a plane, it's just got to be the flux through that shape in the plane. I mean, if I got a plane here and I've got some funky shape in there, isn't it just the flux through that flat surface? Well, you could certainly do it that way. But who says that all surfaces, all loops have to lie in planes? Loops can be deformed. Loops can lie, it can be non-flat. It could be that a loop simply doesn't sit in a flat surface. And once a loop doesn't sit in a flat surface, then what kind of surface are you going to draw through that loop? Well, there's lots of surfaces that you could draw. You could have any surface, any loop we want that's been deformed in all sorts of ways. And we could draw a surface coming out of it, like when you're blowing bubbles, and you take that little thing and you dip it into the soap, and then the bubble is coming out of it, and it could be deformed, or it could be like a parachute, right? And we know that this turned out to be true for any surface. And for something like that now, we've got these little differential elements of area, dA. And the length of dA is just the area of the element. And the direction is equal to a normal vector, all right, a vector perpendicular to the surface. And let's just do a few classic examples in 3 different coordinate systems to refresh our memory on setting up surface integrals. First one, we're going to put something along the z-axis, x, y, z. Right, we've got a surface that's sitting here. And let's say that we have a vector field of the form F equals R vector over R length to the n, or x hat plus y hat plus z hat over x squared plus y squared plus z squared to the n over 2. We often get forces like this when dealing with the interactions between molecules. They're not always of magnitude 1 over r squared. Van der Waals forces are often 1 over r to the 6th. So let me ask you, what would be the differential element of area? If I want to have a little square coming up out of that surface, perpendicular to the surface, I need to somehow write dA in terms of dx and or dy and or dz, and I need to specify its direction in space. So who can tell me?
Well, you need an equation for that plane, don't you?
For the what?
For the plane, so that way we can
Yeah.
find the normal vector on D.
Okay, so this plane, well, this plane is perpendicular to the z-axis. So z is a constant. So what can we say right away about the orientation or the direction of dA?
It's in z hat.
It's in the z direction.
Thank you. Now, I'm going to be integrating in this plane. So I'm going to be integrating from x min to x max. Oh, sorry, that was wrong way. All right, so I'm going to be integrating from x min over here to x max. And I'll be integrating from y min to y max. So in my integral of f dot dA, what are the differentials that I'm multiplying by some component? I've got f dot z hat times d something and d something. D what and d what? Don't overthink it, for the love of God.
Dx and dy.
Yeah, because I'm integrating from x min to x max, y min to y max. Now, the actual doing of that integral could be quite complicated, depending on the form that, that the denominator takes. But we would just have, in general, from x min to x max Any questions on how I set that up? Now someone comes along and says, well, I don't want to do that integral in a finite square region perpendicular to the z-axis. I want to integrate over a sphere. Okay, so I'm going to work in spherical coordinates. We've got our theta here. We've got our phi here, x, y. Now what's dA in spherical coordinates? Someone besides my handful of usual suspects try to tell me what is the direction of dA and what is its magnitude. And remember, this was on Monday's assignment based on the reading.
The direction is in the r hat direction,
Very good.
and the factor is r squared sine theta d phi.
Yep. It's just what we always have when we integrate in polar coordinates and we're integrating over a surface. Some of you may be thinking, what about the dr? The dr would only come if we're integrating not over a two-dimensional surface, but in 3 dimensions, because we want it to go out to larger and larger spheres and integrate over an entire volume to encapsulate a range of spheres. But if we're just integrating over one, it's just going to be f dot r hat r squared sine theta d phi from phi equals 0 to 2 pi, theta equals 0 to pi. And because sine theta d theta is cosine theta, it is often convenient to write this as the integral from phi equals 0 to 2 pi cosine theta equals -1 to +1 of f dot r hat r squared d cosine theta d phi. Any questions? One last example, and this one shows up a lot when doing magnetism, integrating fields around wires or something. Now we're integrating over the exterior of a cylinder, and we'll worry about the caps of the cylinder some other time. Now our dA is here. And so in cylindrical coordinates, what would this be?
R d theta, well, r d phi hat.
Phi hat? If we were integrating around the edge of it, if we were integrating, we're not talking about a line integral. If it were, what you're talking about, Jason, is this. If we're doing a little element like this, this does indeed have length rho d phi, and it has direction phi hat. But now I'm talking about a little element sticking out. So this part of it, this little segment here, is indeed rho d phi. But this segment, the length of this segment, if we're talking about a little square, well, not square, but a little patch on the edge, you're right, one dimension of it is rho d phi. But there's another dimension that we need to multiply by to get the area. And it's not in the phi hat direction because phi has going around the edge. It's sticking out. What's a unit vector sticking out? So rho d phi, d something, something hat.
DZ, Z hat,
What?
DZ, Z hat.
Z hat, if you just think about the orientation, Z hat is going this way. But you're right, it is dz for the length. The length is indeed along this direction. But Z is in that is along the axis. I want something sticking out. We've tried z hat, that didn't work. We tried phi hat. What's the third unit vector?
Would it be the radius of the?
Rho hat. Rho hat is sticking out from the axis. All right. So now we're going to have the integral from z min to z max, and the integral from phi equals 0 to 2 pi of f dot rho hat rho d phi dz. Any questions? All right, I'll have you do some of these on Friday in the activity. I'll have you actually crank through some of the integrals on Friday. For now, I want to show you a theorem that is used less for calculating very specific surface integrals than for deriving facts. It's called Stokes' theorem. And Stokes' theorem says that if we have a closed loop, we've got some surface whose boundary is along that loop, and that surface could be flat or it could be bulging out, could be like, you know, when you're blowing bubbles, could just be flat, but whatever it is, the integral of f dot dr along that surface, or the integral of f dot ds, some people write it, is equal to the integral over the bounded surface of the curl of f dotted with dA. And people use that. I mean, somebody somewhere has at some point said, all right, I've got this line integral that I can't do, but I can do this, the surface integral if I just take the curl. Somebody somewhere has done that. It's a big world. I'm sure that somebody has at some point done that. Where I almost always see it used, though, is less for calculating a particular integral than for doing a derivation. For instance, Faraday's law. The line integral around a closed path of E dot dr, which is just the energy gained by a charge moving along, it's the work done on a charge by the electric field going around that circle, the work done on a unit charge, I should say, is equal to the minus the time derivative of the magnetic flux. And we know we can turn this into the integral of the curl of E by Stokes' theorem. And two integrals, the fact that two integrals are equal to each other does not automatically mean that the integrands are the same. If two integrals were equal to each other when working over some particular domain, but then as soon as you change the surface you were integrating over, these two integrals were no longer equal, well, that's not terribly useful. But if two integrals are equal to each other for any surface that you do, then they have to have the same integrand. If they're equal to each other no matter what, then the only way this can work is if they have the same integrand. And so because of that, we can equate the integrands minus partial b partial t equals the curl of E. And there are various types of units at E and M. This is not going to be any homework or test in here, But there's everything from very childish units like SI or CGS, which I both consider to be childish units, to teenage young adult units where you would have -1 over C partial B partial T equals curl of E. And I call those teenage young adult. You're a little more mature because now you've got 1 over length multiplying the field on both sides. You've got 1 over C dt. C dt has units of length. And then the curl has units of 1 over length because you're taking derivatives with respect to X, Y, and Z. So now B and E have the same units. And as you get more mature, you realize the electric and magnetic fields are manifestations of the same thing. So they really should have the same units. It's only in childish units like SI that they have different units. Now in CGS, they have the same units, but CGS has these stupid 4 pi's running around and nobody needs extra 4 pi. But then you get more mature and you realize, wait a minute, C is just 1 because calling C anything other than 1 means that you're measuring velocity in units that aren't natural for the universe. But don't, that's just an aside. So that's one result that you could derive using Stokes' theorem. And it's a pretty important result. But let's talk about another result, which so far I've just been asserting. If del cross F equals 0, for all points in space, then F equals minus, or F just equals, I'll just say the gradient of some scalar function S. All right, now not just if del cross F equals 0 at one point in space. Something could always have 0 derivative somewhere. And if it has 0 derivative somewhere, well, that doesn't mean much. But if it has 0 derivative everywhere, then let's construct a path, a closed path. And along that closed path, I'm going to pick out 2 points, A and B. All right. I'm going to have segment 1 and segment 2. Then the integral of f dot dr, I could write that as the integral from A to B along path 1, f dot dr, plus the integral from B to A along 2, f dot dr. And that's just from the fact that it's a closed path. Or I could say that that is the integral from A to B, f dot dr along 1, minus the integral from A to B, f dot dr along 2, because whenever you reverse the limits of integration, replace A with B and B with A, then you just multiply the integral by a minus sign. Here's the thing, it's also got to be, according to Stokes, the integral of the curl of F dotted with dA. That's what Stokes says. But what is the curl of F according to the assumption here?
It's 0 at all points.
So that means that these two integrals are equal. These two cancel. And furthermore, I could have picked any other path. I could have picked, instead of paths 1 and 2, I could have picked paths 2 and 3, or 1 and 4, or 3 and 4, or whatever. I could pick any pair of paths I want. I could, construct some monstrosity of doodling. It looks like something from a Lovecraft story. And again, I would get the same result going from A to B, no matter how I do it, right? No matter which pair of paths I choose, I will get the same result going from A to B. So what I can conclude is that if del cross F equals 0, for all points, then the integral from A to B of F dot dr is just some function that I'm going to call S of B minus S of A. And the reason I'm saying that is because I've got this integral whose value doesn't depend on the path. It only depends on start and end. Only depends on the start and end points. So that's really the only form that it can have, all right, is the difference between values at the start and end. And then that means that this is the gradient of S. Just like if I had in one dimension that the integral of f dx is equal to S of x2 minus S of x1, then we would immediately know that F is the derivative of S. So this is just a generalization of that. If you wanted to be a bit more rigorous, I would say that the integral of f dot dr is equal to the integral of the gradient of s dot dr. So the integral of f minus gradient of s dot dr equals 0. And it's equal to 0 for all paths. If the difference between two things dotted with a third thing is 0, that doesn't automatically mean that the two things are the same. If I've got two vectors which are very different from each other, but happen to have the same x component. So I subtract these two vectors. All right, if I have this only implies f minus gradient of s equals 0 if true for all paths. If it was only true for a few paths, let's imagine I've got two vectors, A and B. A and B are different vectors, but lo and behold, they just happen to have the same x component, right? Here's my y-axis, here's my x-axis. A and B have different lengths, they have different directions, but they happen to have the same x component. A minus B is not equal to 0 because they're different vectors. I subtract them, I can't get 0. But A minus B dot x hat equals 0. So here's a case where this statement is only true for one particular value of the third vector. I subtract two vectors, dot with a third, I get 0. But those first two vectors are not equal to each other. But if it were the case that C minus D, two other vectors, dot x hat equals 0, and C minus D dotted with y hat equals 0, and C minus D dotted with z hat equals 0, well, then I know that the x component of their difference is 0, and the y component of their difference is 0, and the z component of their difference is 0. And then I know that they must have the same x component and the same y component and the same z component. Then I could say that they're the same vector. And likewise up here, this statement that the integral of f minus grad s, whole thing dotted with dr equals 0, this implies f minus grad s equals 0 or f equals grad s only because it holds true for all paths. Questions? I went through a subtle argument. Someone must have a question. You know, in a class like this, there's two very different levels of things that we're doing. There's what I'm actually going to test you on, what I'm actually going to grade you on. And what I'm actually going to grade you on and test you on is the stuff that's in the homework. And all of that is stuff that you will see in subsequent classes, at least in some form. I mean, I'm not saying that somebody's going to immediately write down in mechanics, xy, x hat plus xy, y hat is your vector field. Is that a conservative field? But you know, they're going to give you specific vector fields and ask you, are these conservative? Are they gradients of scalar fields? And then there's the meta lesson. How does one argue things? How does one establish things? And that I don't test on as much. That's more of a meta lesson that comes from many years of watching physicists do things. And some will say that that watching physicists do things is the wrong way, that it should be you guys talking to each other. But the truth is you only learn how experts reason by paying attention to experts as they reason. No one has ever learned how experts reason by listening to a non-expert reason. So I'm going through a subtle argument here as part of the meta lesson. What I'm actually going to test you on is on the homework, and that's stuff that you will see in future classes. But then there's also the meta lesson of how do we establish these things? How do we think about these things? Are there any questions on that?
Professor, I mean, I'm just trying to get a handle on what we just went over. And are you saying that if the gradient cross f is 0 for a closed line integral, then we have f dot dr, which is equal to s of b minus s of a?
No, I'm not saying that if the gradient is 0 for a closed line integral. I'm saying that if the gradient, I'm saying that if the curl of f is 0 everywhere in a region of space, then the line integral along any closed path in that region is 0. And if the line integral over a closed path in that region is 0, then the line integral from one point to another in there must be the same for all paths. And if that line integral is the same for all paths from A to B, then f is a gradient.
So how do we show that the curl of f is 0 for all points? Like, would you just give us a generalized equation for f? And if we take the curl of that equals 0, would that suffice in saying all of the points are 0?
I mean, you just look to see if things cancel. Like, look, let's say that f is equal to x times x hat plus y times y hat plus z times z hat. All right. Then the curl of f, don't make this hard. All right, do not make this hard. The curl of F is just, oops. I mean, look, in this problem, we're going to get x hat times partial z partial y minus partial y partial z minus y hat times partial z partial x minus partial x partial z plus z hat times partial y partial x minus partial x partial y. I mean, you just take the derivative, and if it comes out to be identically 0 for every x, y, and z, then the curl is 0 for all x, y, and z. Right? And sure enough here, derivative of z with respect to y is 0. Z doesn't depend on y. Derivative of y with respect to z is 0. Similar here, similar here, similar here, similar here. Boom, the whole thing's 0. That's all. That's all I'm saying.
So then you're saying,
Yes, Sebastian?
so the curl implies that you are evaluating all points in space just based upon the function itself?
No, look, I could suppose that I calculated the curl. All right. Sometimes the curl comes back 0. What if, and I'm just going to make something up right now. What if the curl of F turned out to be cosine A cosine KZ X hat? All right. That's a curl you'll see a lot. That shows up in the theory of waves a lot. You tell me, is that 0 everywhere in space?
No.
Okay. Don't make this hard. Don't make this hard. I mean, I realize that working with symbols is considered hard because I guess we've learned absolutely nothing since the Sumerians and Egyptians first realized that you could do things writing with symbols. Okay, but people have been working with symbols for a long time. Well, not everyone. I mean, much of Europe was barbarian back when the Egyptians and Sumerians were working with symbols. Okay, but still, you know, the people have been working with symbols for a long time. Don't make this hard. All right, you just take a curl and you look at it, and does it come back as some complicated function that'll be 0 in some places and non-zero in others? Well, then the curl isn't 0. Does it come back as just the symbol 0, which admittedly the Sumerians and Egyptians didn't really have, but at some point they got it in India and then it spread over the world? Yeah, all right. If it comes back 0, it's 0. If it comes back some complicated expression that's sometimes 0 and sometimes not, well, then it's not 0 everywhere in space. Don't make this hard.
All right, that's what I was getting at. It's a cool thought to think that just a curl of a function, you are testing all points in space, whether or not it will be 0.
Okay, I mean, I get a lot of people say like, Professor, I got this function, and I'm not just picking on the 2 of you. I'm not even picking on the 60 of you, okay? Because I've been teaching for a long time. I've had a lot more than just the 60 of you. And people come to me and say, so Professor, like I calculated, you know, the curl, and like it came back as like cosine of KZ, and like, is that 0? And I'm like, well, you tell me, plug in different values of K and Z. Well, like sometimes it's 0. Okay, but is it always 0? Well, like, no. Well, then like, it's not everywhere 0. Boom, doesn't satisfy the assumptions of the theorem. Get used to working with symbols. They've been doing this for 5,000 years. They started doing this as soon as they had an agricultural surplus. As soon as someone figured out how to grow enough wheat, boom, people started working with symbols. And if there's one thing the modern world does not have a problem with, it's an excess of carbs. We have at least as much excess grain as anyone in Sumer in Egypt ever had. Okay, we got enough grain to work with symbols here is what I'm trying to say. And if it seems like I'm obsessed with the ancient Middle East, it's because I'm working on my Epic of Gilgamesh cyberpunk game for the physics club in a few weeks. Okay, so that's one theorem, and we can use it to prove a few important results, like taking Faraday's law and deriving a differential equation from it, or taking a field that has zero curl everywhere and deducing that that field must be the gradient of a scalar function. Now let's talk about another theorem, the divergence theorem, which is useful for understanding, say, Gauss's law, and then on next week's problem set, you're going to use it to understand conservation laws. The divergence theorem says that if we have a closed surface, with the double integral over a closed surface of f dot dA is equal to the integral over the enclosed volume del dot f dv. So you've got some closed surface. We compute, we have a whole bunch of different places where we just keep computing f dot dA. And over here, we've got another dA, sorry, another value of f. And we could integrate over the entire enclosed volume del dot f. And these two things are the same. Now, Gauss's law says that the double integral of E dot dA is equal to the enclosed charge. And I'm working in Heaviside Lorentz units, which are, of course, the units that God used on the first day when he uttered Maxwell's equations, and behold, there was light. God did not utter them in SI units, which have these epsilon naughts and mu naughts, for epsilon naught and mu naught are abominations in his sight, nor did he use Gaussian or CGS units, which have these 4 pi's, which would be unholy in his sight. He obviously did them in Heaviside Lorentz units with C equals 1. That's just obvious. Now, the enclosed charge. Well, you told me if I want to figure out how much charge is in a volume, what is a physical quantity that relates the amount of stuff in a volume to the volume?
Charge
Density.
Yep. This is a volume integral of rho dV. But we know from the divergence theorem that this is del dot E dV. And we know that this is true for any surface and the corresponding enclosed volume. Whether I want to draw a really simple surface like a sphere around the origin, or a cube around the origin, or a cylinder, or some many tentacled beast from a Lovecraft story, whatever kind of surface I want to draw, this still holds. So del dot E is equal to rho. Any questions? The divergence theorem is sometimes used to simplify integrals, but it's also used just to derive results, to relate what's going on at a boundary to what's going on inside. I'm going to give you a little preview of something on the next problem set. If I've got a surface, okay, I've got stuff inside, labeled with the very formal name stuff. Well, some of this stuff is escaping, okay? So J is a vector whose length is the flow rate. His direction is the direction of flow. Stuff. Okay. So the integral of j dot dA must be equal to the rate of stuff leaving. And if stuff is leaving, that's stuff. I'm saying, you're wondering, why is he saying stuff? Well, because the same logic applies whether we're talking about the flow of mass, say fluid flow, or the flow of not mass, but the exchange of chemical species, diffusion, where you got an incompressible fluid, you got molecules diffusing it, you just replace one type of molecule with another as things diffuse around. I could be talking about the flow of energy. We're talking about equations for the flow of light. I could be talking about the flow of even momentum in certain kinds of fluid dynamics problems. But the flow of stuff, and the integral of j dot dA is the rate of stuff leaving. Well, if stuff is leaving, that's positive. If there's a positive rate of stuff leaving, then the density or concentration is decreasing. And so we can relate this integral to an integral of density or concentration, which is what you do on the next problem set. And then we could use the divergence theorem to get a differential equation. And that's what you're going to do on the next problem set. This is where the divergence theorem is used the most in derivations. Now, the divergence theorem also leads us to a surprising result. Okay, we know that del dot E is equal to rho. Now, let's say we've got a point charge at the origin, point charge Q. Well, if I'm out here, tell me, when I'm somewhere away from that point charge, what is the density? Not the average density over all space, the density right here. What is the density there? What's the charge density? Don't overthink it. Is there any charge there?
No, there's no charge there.
Zero. So charge density is zero. Rho equals zero here. Rho equals zero here. Rho equals zero here. Even right there, rho equals zero. Rho is equal to zero everywhere except one point. If the integral of rho dV is non-zero, okay? So for point charges, we use something called the Dirac delta function. The Dirac delta function is a very special function. Delta of x equals 0 if x is not equal to 0, infinity if x equals 0, and the integral of the delta function is 1. And it's usually written very formally like this. But in general, I could write it as the integral from a to b of delta of x dx equals 1 if a is less than 0 and b is greater than 0. -1 if a is greater than 0 and b is less than 0. That would just mean that instead of going from left to right, we're going from right to left. And 0 otherwise. So if I go over this interval, likewise, if I go over this one, the integral of delta of x dx equals 0. But if I go over this interval, right? It's a function that drives mathematicians crazy. It's a function that mathematicians hate. They say it's not really a function, it's some other type of mathematical object called a distribution, which is not quite the same as a probability distribution. We physicists simply use it. This is one of those things where we say to the mathematicians, we don't care. There's actually, if you've ever heard of the Millennium Prize problems, there's a set of once upon a time 7, now 6 math problems that are considered holy grails of math. Solve any one of these problems and you get $1 million. One of them was solved shortly after the prizes were announced. 2 of them involve not the delta function, but they involve proving that certain equations in physics have solutions. And physicists have been solving these equations for a long time and saying, hey, it works. And the mathematicians say, prove rigorously that it works. And we say, I don't know, the numbers we get out match the experiments. Yeah, but how do you know that you followed honest methods to get those numbers? And the physicists say it works. So physicists like making mathematicians cry. It's something we're good at. We do it a lot. Just as physics students enjoy making me cry by not doing math correctly, physicists enjoy making mathematicians cry by doing math in ways that I would say are close enough to correct. And mathematicians would say, still not good enough. The delta function, the best way to think about the delta function is this. I think of the delta function as the limit of a sequence of functions. Here's a function that has some width. I'll call this f1, it has width w1. And the integral of f1 of x dx from minus infinity to infinity is 1. Here's another function, f2 with width, smaller width w2. And the integral from minus infinity to infinity of f2 of x dx is also equal to 1. And then I could go with a really narrow function. F3 with width W3. And the integral of F3 of x dx equals 1. And the delta function would be if we just kept on making it smaller and smaller and smaller. Fn, it has width Wn. All right, the integral from minus infinity to infinity, Fn of x dx is also equal to 1. Wn is going to 0. So Fn is going to 0 for x not equal to 0. And it's going to infinity for x equal to 0. Because as we keep making this function smaller and smaller, narrow and narrower, we decrease the width, we keep the integral or the area under the curve the same, which means the function has to shoot up at the origin. All right, that's the delta function. And the delta function gets used, well, obviously in E&M or gravity to talk about point particles, because a point charge has infinite charge density. A point mass has infinite mass density. So we use delta functions to talk about point particles. We're going to use delta functions in a couple weeks when we do Fourier transforms. to talk about pure frequencies. The way to think about a pure frequency is that we have a finite amount of energy squeezed into zero frequency range, okay? Somehow you've got a range of frequencies with zero width. You got a spectrum with zero width, and we have all of the energy at that point on the spectrum. So the spectrum must have infinite energy there, zero energy everywhere else. So we're going to use that in Fourier transforms. Now, the reason it's relevant to vector calculus is that del dot r hat over r squared is delta cubed of r. Okay, this is just a way, delta cubed is just the 3D delta function. It just means that the integral from x equals minus infinity to infinity and y equals minus infinity to infinity and z equals minus infinity to infinity of delta cubed of x dx of r, excuse me, dx dy dz equals 1. Questions? Let me tell you one more fact about the delta function, which we can also understand in terms of E and M. Del dot E must be equal to Q delta cubed of R. And you're thinking, why Q times delta cubed? Well, if I integrate the charge density, I shouldn't get 1 unless the charge happened to be 1. I should get Q, all right, where Q is whatever that charge is. Q might be +1, might be -1, might be -1/3, might be 1.6 times 10 to the minus 19 coulombs for an electron, whatever. Sorry, that would be a positron. It would be -1.6 times 10 to the minus 19 for an electron, but you know what I mean. Now, E is minus the gradient of V, okay? So del dot E is del dot minus the gradient of V, or minus del squared V, which is Q delta cubed of R. And we know that for a point charge, V is Q over 4 pi R. There's no epsilon naught in God's own units. So what we've got is that minus Q over 4 pi del squared 1 over R is equal to Q delta cubed of R. Cancel out the cube, and we get that the Laplacian of 1 over R is equal to 4 pi delta cubed, sorry, minus 4 pi delta cubed of R. This is not a problem set. It will be on problem sets when we get to Fourier transforms. But for now, this is just one of those things you should know about. The delta function is this function that's 0 everywhere except the origin where it's infinity. When you integrate it, you get something finite. And it shows up anytime you're talking about point particles. So any formula we've derived involving point particles, anytime we've taken the divergence or the Laplacian of it, strictly speaking, those things were only valid away from the origin. We can use this in the remaining 60 seconds to make some sense of something you saw on Friday. Remember on Friday, we had the magnetic field of a wire, right? And we got that the integral of B dot dr going around this path was non-zero. strictly speaking, we didn't call it B, we called it phi hat over R. But the curl of phi hat over R was equal to 0. All right, the thing is that when you took the curl of phi hat over R, at some point what you actually got was R times 1 over R. All right, R times 0 over R. And 0 over R, if R is non-zero, then 0 over R is just 0. But if we had done it much more carefully, what we would get is that the 0 on top was changing slowly, that the thing on top was approaching 0 slowly. And the thing on the bottom, when R is 0, is approaching 0 rapidly. And so you get 0 over 0, which is really infinity. Okay, so R times 0 over R goes to infinity as R goes to 0. In this case, I'm using a shorthand for a much more elaborate process of taking R to 0. And that is why del cross phi hat over R is 0 everywhere, or phi hat over rho, I should say. And it's a delta function, a 2D delta function when rho equals 0, when you're on the axis. So that when we integrate over the entire plane, we're integrating a current density. That way the integral of J dot dA, current density, is equal to the current even though J equals 0 off axis. Questions? This was all just for your edification. We're done for today. On Friday, we will do some surface integrals during the activity. And then next Friday, there will be a midterm covering the problem sets, covering problem sets 5 through 8. See you Friday.
Thank you, Dr. Small.
Mm-hmm.
Thank you, Dr. Small.
Thank you, Dr. Small.
Bye.